积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高锟推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花。
OK， 开始了。
Okay, so good evening. Welcome to the seventh talk of the course series of the fundamentals of integrated sensing and communications. So today we are very happy to invite Professor Andrew Zhang from University of Technology Sydney, Australia, to give us a lecture on the bistatic sensing with clock asynchronism. So before Professor Zhang's talk, I would like to have a brief introduction of Professor Zhang. Actually, I believe all of the audience should have known Professor Zhang very well. So currently, Professor Zhang is a professor in the School of Electrical and Data Engineering, the UTS, Australia. Actually, Professor Zhang is one of the pioneering researchers in ISAC. So he has significantly contributed to the community education and also the technical dissemination of ISAC technologies. So Professor Zhang currently have delivered 6 tutorials, more than 15 keynotes, and numerous invited talks and webinars on ISAC. Currently, he is leading the publication team of the IEEE ComSoc ISAC ETI. He also served as the editor-in-chief of the ISAC ETI newsletter and served as the co-chair of the ISAC Special Interest Group within the IEEE GC-TCC. So today, Professor Zhang will give us a talk on the bistatic sensing with clock synchronism. So in this talk, he will explore advanced techniques to address the clock synchronism challenge in bistatic sensing with a focus on efficient solutions, right? Require only a single receiver. Okay, so let's welcome Professor Zhang to give this wonderful talk.
Okay, thank you very much, Weijie, and I would like to thank Chess Park for offering this opportunity. I'm pleased to share with you some of our research experience on bistatic sensing. When we say bistatic sensing, we mean the receiver, the sensing receiver, and the transmitter, they are geographically located separately. And not like a bistatic, monostatic sensing, the transmitter receiver, they're co-located. So in bistatic sensing, typically there's a major issue when we refer to the communication system, which is called clock asynchronism. I'm going to discuss the details shortly. So I would like to discuss the bistatic sensing problem by referring to what we call the perceptive mobile network. Essentially, this is about realizing integrated sensing and communications in the mobile network. So I will provide a quick introduction about my lab first. So we initiated the concept for perceptive mobile network back to 2017. And then since then, we published a series of papers, about now 70 top journal papers. And we have attracted about 8.5 million Australian dollars research funding. Importantly, we created a network sensing joint research lab with a local mobile network operator, TPG, in Australia, and we try to commercialize the technology in the real mobile network. Okay, before we discuss the details about biostatic sensing, I think it's important to have a look at the major differences between radar communications and ISAC systems. We know there are a lot of differences. For example, the signal bandwidth is very different. Radar has very large signal bandwidth, while communication typically has only like tens to maximum hundreds of megahertz. And also the signaling scheme is very different. OFDM versus, for example, pulse radar or chipped radar. But there are actually two major differences here from my point of view. One is called monostatic setup versus bistatic setup. So we know in real applications, many radar systems, they are monostatic, right? As I mentioned, the transmitter receiver, they are co-located in one device. So in this scenario, the radar uses echo signal of the transmitted one for sensing. And this particular setup typically requires capability called full-duplex. Right? Full-duplex means we need to be able to transmit and receive at the same time. Right? So this capability doesn't exist in current communication systems, although people have been investigating hardly, try to realize full-duplex communication, but still we haven't seen any practical commercial system yet. So this is a very challenging problem. So to realize sensing in communications, if we refer to the typical radar approach, then we need to realize full duplex. But currently, as we just mentioned, it's not commercially available yet. Another approach is called bistatic. So in bistatic, transmitter receiver are separated, and this actually perfectly matches the topology in communication networks. Right? We know in all of the communication system, transmitter and receiver, they are separated. But a bistatic system, they have a major issue. It's called clock or local oscillator asynchronism. So this means there's no common locked clock supporting the transmitter and receiver. And this asynchronism causes major issues when we do sensing. We are going to discuss the details shortly. So anyway, the monostatic setup requires full duplex, and the bistatic doesn't, but it faces the clock asynchronism issue. Right? So these are the actual most challenging issues when we want to realize sensing in communication networks. So come back to perceptive mobile network. There are typically three approaches if we talk about sensing from the base station point of view. Of course, we can also realize sensing from the mobile terminals, but base station, it has much powerful capabilities compared to mobile phones. For example, it has a much larger antenna array. We know each antenna is just like one pixel in a camera, right? So more antennas means we have more pixels. We can achieve better resolution, particular spatial resolution. And more importantly, a base station sees hundreds or even thousands signals from the mobile phones, right? So this means because each mobile phone and the base station, they form a pair of radar, right? So this means each base station, it sees hundreds and thousands of radar if we do sensing at the base station. So this is very promising. It means almost a ubiquitous sensing network can be realized if we do sensing at the base station. Right? So we focus on the base station side sensing in this talk. And there are three types of sensings. One is called standalone base station-based sensing, and it can based on two approaches. One is like a monostatic setup. So the base station uses its own transmitted signals echo to do sensing, and this requires full duplex, right? And another one is like a bistatic sensing. It uses the uplink communication signals for sensing. This is the bistatic setup. It doesn't require full duplex, and it can actually be easily realized if we can resolve the clock asynchronism issue. And another one, more advanced, it's based on distributed system. Suppose we have multiple receiving antennas, and they are connected, and this corresponding to, for example, the cloud radio access network, right? So the base station is centrally located, and the base station connects to multiple distributed antennas. In this scenario, we can jointly process the signals from multiple antennas and do sensing. In terms of the actual sensing, we can share a lot of the receiving structure as shown here. This shows a typical OFDM or MIMO OFDM receiver. So most of the processing can be shared by sensing functions. And for sensing, we can use two types of signals or even three. The most typically used one is called channel state information. Right? We use the pilots do channel estimation and then use the channel estimates for sensing. So this is a simple and a straightforward approach. We can also use the data payload, for example, for sensing, but this involves more complicated processing. In this talk, I will mainly consider the first type of sensing approach, use the channel state information for sensing. Okay, because full duplex is not commercially ready yet, so we needed to consider the near-term solutions, maybe they are not ideal, but these approaches allow us to realize sensing in the near term and at an approach without requiring significant network modifications. Right? So among them, one of the most promising approach from my point of view is doing uplink sensing using the uplink communication signals. The advantage is, as I just introduced, right? Not only it aligns with the communication infrastructure very well, and it can be realized without requiring major modifications to the network, and it can also enable hundreds to thousands of radar pairs for each base station, right? So it implies a huge sensing diversity in this scenario. Okay, then how can we realize biostatic sensing using uplink communication signals? We can have a look at the basic signal models. This is the expression for the channel state information. All right, this is a time domain. This is the frequency domain at the nth subcarrier. So the blue variables represent those that we are interested from the point for sensing. Right. We're mainly interested in delay, propagation delay, Doppler frequency, the two angles, angle of departure and the angle of arrival, right? Sometimes we're also interested in the amplitude as well. So most of the sensing applications, they explicitly or implicitly based on these parameters. Right. So for example, for localization, we typically need to know propagation delay, which determines the range, and these two parameters related to the angle of the object. And for other sensing applications, which are quite often based on, for example, the Doppler shift, etc. Right? They may not require the propagation delay, etc. So anyway, most of sensing, we needed to estimate these sensing parameters. And these three red variables, they represent the offsets associated with the clock asynchronism. We are going to discuss their impact on sensing shortly. These two signal models or channel models, they are actually already known in communications. For example, in millimeter wave systems, right, we often estimate the structure of this channel instead of the channel elements directly, because in, for example, massive MIMO, there are so many coefficients to be estimated. If there are only a limited number of multipaths, then we can estimate these sensing parameters directly and then get the channel matrix. Right? So we have already seen such problems, similar problems in communication systems. But what make the sensing challenging in uplink sensing is these offset terms, right? Okay, so let's have a look at a general problem of sensing using communication signals before we dig into the details of biostatic sensing. So as I mentioned, actually, sensing parameter estimation not really very new issue. All right, we have already seen research works 10 years ago when we do, for example, particular millimeter wave for system research, and the major challenges when we try to estimate all these parameters are in communication systems, resource allocation cause fragile or discontinuous observations in time, frequency, and space domain. This is associated with, for example, subcarrier location, time slot allocation, and antenna allocation in 5G NR system, right? So we face many non-continuous measurements, and we also face complicated resource allocation. Then how we can do sensing using these non-regular observations? So this is the fundamental challenge we face with the general sensing without considering clock asynchronism. Right? Here is a signal model representing the MIMO OFDM plus SDMA realization. Right? So this is probably one of the most complicated signal expression. And based on this signal expression, even we, without considering more complicated processing approaches, we can already estimate these parameters. In terms of the actual approaches, there are probably two typical ones. One is called indirect sensing, another we call it as direct sensing. Indirect sensing means we first decompose the received signal. For example, we remove the transmitter symbol, we decompose signals to each user in the SDMA or FDMA scenario, etc. Right? So this means we try to make the signal as simple as possible, or directly get the channel state information for each user, and then we apply sensing algorithms. This is called indirect sensing. Direct sensing means we do not separate signals. We directly use the receiver signal for sensing. So these two approaches, they have respective advantages and disadvantages. We will have a brief discussion next. There are a few issues here. So when we do sensing, typically we face the scenario that Doppler has the fastest change, right? Change rapidly, and delay and angle, they typically change much more slowly. So this means in many sensing applications, typically we estimate Doppler using a small segment of signal, and then during this period we can assume delay and AOA, they are unchanged, right? So this is a typical strategy we can use. Okay, so for direct sensing, as we mentioned, we do not separate the signals. We directly use the signal for sensing. So this approach has several advantages. For example, it won't cause additional delay which is associated with the separation process. And we can develop statistical optimal algorithms because there's no information loss during the process, for example, separating signals, etc. But it does have a major disadvantage. So typically, if we are not talking about, for example, correlator-based sensing, the complexity of such algorithms would be very high. Because if we go back to this equation, it is indeed quite complicated. It has symbols, has multiple signals from multi users, etc. Right? So there's no simple ways to do sensing if we adopt the direct sensing approach. On the other side, if we want to do indirect sensing, we need to decompose the signal, we need to remove the transmitter symbol, etc. So we need to involve some additional processing before we can get the channel state information. For example, this is a typical operation similar to the zero forcing equalization in communication system, because we needed to compute the inverse of the training symbols or the data symbols, and then get the channel estimates. Right? So this would have a similar issue that we face for zero forcing equalization. Noise enhancement. If the data symbol matrix doesn't have a good property, for example, not orthogonal, then we will have a lot of noise in the channel state information. So indirect sensing is more useful when we use the channel estimates from the pilots, because in this scenario, the pilots typically they are orthogonal. All right, we want to have noise, enhance the noise in the estimated channel state information. Okay. Nowadays, most of the sensing is based on the indirect sensing approach, right? Or we get the channel estimates first and then do sensing. So in this scenario, actually, we can get equation called 4D harmonic retrieval problem, right? So we have these unknown parameters, delay, Doppler, angles, all in the exponential functions. Then this is the sum of the or the path. So this problem can be solved by many well-known techniques. The simplest one is the parallel diagram approach. Essentially, this is AFT, DFT-based approach. And more advanced one, including these ones. The parallel diagram one, it has the lowest complexity, but the resolution is also low. Typically, it's limited to the symbol period, etc. More advanced techniques, for example, the subspace-based ones are most typically used ones. It includes Esprit, music, etc. We can also use, for example, compressive sensing, etc. So these approaches, they are powerful in the sense that we can incorporate the prior knowledge into the sensing parameter estimation. While subspace-based approaches, they are typically the deterministic ones. They are not a statistical approach, so it's hard to incorporate prior information for the sensing parameters, right? Okay, now let's come to the major topic today, biostatic sensing. So as we mentioned, when we estimate the sensing parameters, we're facing these offsets, phase offset, delay, timing offset, and the carrier frequency offset. So in the sensing system, when we base the signal on the channel state information, typically we already applied some channel, for example, carrier frequency offset estimation during the communication stage, right? But the carrier frequency offset term here we are referring to typically means the residual carrier frequency offset. For communications, we don't care about this too much because its impact can be compensated by using pilot embedded in data symbol. We then estimate the phase rotation caused by the residual carrier frequency offset, right? And then compensate for its impact. But for sensing, if residual carrier frequency offset is unknown, then it will introduce some ambiguity in Doppler frequency estimation, because this value, the value of the residual carrier frequency offset is comparable to the Doppler frequency. Typically, the Doppler frequency ranges from tens of hertz to a few kilohertz in most of the applications. So the residual carrier frequency offset is in the same order with the Doppler frequency of interest. So we have to know it or remove it. Otherwise, it will cause issue when we estimate Doppler frequency. Timing offsets is similarly not a problem in communication system because we can absorb the timing offset into integrated one with the propagation delay, and then their impact will be combined into the channel estimation. But for sensing, if we do not know the timing offset, then it will cause a ranging ambiguity. All right? And the phase offset, it can be an independent parameter, or it can be partially related to these terms. The phase offset, they can prevent coherent processing in sensing, because if each measurement, each observation has an unknown random phase shift, then we cannot use the phase for sensing, right? Because the phase is unknown, and we can only use, for example, the power for sensing. This immediately leads to at least a 3 dB degradation. So to do sensing properly, we needed to either remove all these 3 unknown offsets, or we estimate and compensate for them, right? So this is a common challenge in almost all of the communication systems if we want to realize sensing based on them, right? Here, the two figures show the actual measured results. This figure shows the phase from multiple or several subcarriers over different snapshots. Snapshots means the measurement over the time domain, right, in the temporal domain. So each color here represents the phase at one subcarrier. As we can see, the phase is slowly drifting, right? And then there will be a sudden change, and then slowly drifting again. So during the small drifting period, the transmitter is transmitting the pilot continuously. So the drifting is slow. But when there's a transition in the transmitter and the receiver state, then there will be larger change. So this causes larger change, and the change is very random. So without knowing this change, the phase offset cannot be removed. And this figure shows the results from Wi-Fi, because Wi-Fi is based on a CSMA protocol, right? So we transmitter, receiver, their states transit quickly. So we can see the phase variation completely random, right? So this indicates such offsets actually exist in practical systems. When we try to resolve the clock asynchronism issue, we not only want to remove or compensate for these offsets, we also want to take the opportunity to remove these non-desired paths, in particular static path. Because for sensing, most of the time we are interested in dynamic path. Static path, they are clusters from the static objects. So typically they are not of interest. So when we're doing sensing, bistatic sensing, removing the offsets, etc., we also try to reduce the number of paths to be estimated so that we can achieve better estimation performance. Let's first look at how this problem is solved in traditional passive radar. In passive radar, the receiver uses signal from another transmitter for sensing as well. All right. Some passive radar, the transmitter receiver, they may use synchronized clock via fiber opticals, but some passive radar, they also don't have such a locked clock. So what they typically do is they use a dedicated receiver to create a line of sight path between the transmitter and receiver, and they use this signal as a reference signal to do some correlation with the surveillance signal to remove these offsets. Right. So this is a typical approach used in passive radar. This approach, it is effective if there's a line of sight path, but it requires a dedicated receiver, right? And sometimes it's hard to find such a line of sight path. So when we try to realize bistatic sensing in communication systems, we want to just realize sensing based on current infrastructure. We do not want to introduce additional reference IX receiver, right? So what we can do? Okay, in the past 7 to 8 years, people have developed various approaches to tackle this issue, and we classify them into 3 types of technologies. So we call them as offset estimation, offset cancellation, and a combination of these 2. Offset estimation means we try to estimate these offsets and then compensate for them. While offset cancellation, this approach doesn't estimate these offsets. It directly cancel them. Right? So we will see quite often these 2 approaches have respective advantages and disadvantages. While offset cancellation can achieve perfect cancellation. It introduces additional terms. And offset estimation, sometimes is more effective, but a major issue is we often cannot get a very accurate offset estimation. Right? So sometimes we also find it's more effective when we combine these two approaches together. So for some offsets, we cancel them, while for some we try to estimate and compensate for them. Earlier techniques, they are based on offset cancellation, and these techniques also started from spatial domain, and then further being extended to delay domain. The spatial domain approach, it includes two typical ones. We call them as cross-antenna cross-correlation and cross-antenna signal ratio. So the underlying idea here is in a receiver, if we have multiple antennas, typically these antennas, they use a fixed clock. Right? So this means the clock offsets between these antennas and the transmitter antenna are identical. So exploiting this property, we can remove the offsets by either multiply signals between multiple antennas or can compute the ratio between them. All right. And there are a few highlights here about these approaches. So these approaches, they can be realized in a single receiver node. It doesn't require the cooperation of multiple receivers. And which one is more efficient? Often it's application dependent. For example, if you only needed to estimate Doppler, offset cancellation could be very efficient and simple, right? But if you want to estimate more parameters, then you may need to consider a hybrid approach. And another different approach, this was introduced a bit later compared to these approaches. And the idea is we create a reference signal like the passive radar scenario, right? We use hardware to create a reference loss path. And here we can similarly create a reference signal from the received signal and use this reference signal to do either offset estimation or offset cancellation. And the latter is more typical. Actually, these approaches, cross-antenna cross-correlation and cross-antenna signal ratio, they are special for the reference signal construction. This means the reference signal is just the signal from another antenna, for example, right? Okay, let's have a look at several techniques in this category. So the first one, cross-antenna cross-correlation, the basic idea is compute the cross-correlation between the signals from two antennas, right? So this is signal at one antenna. Now, if we compute the cross-correlation, we can see all these offsets, they are canceled, all right? But the issue is, originally, we only have unknown sensing parameters associated with the AL path, all right? After cross-correlation, we now have two AL paths. What's worse, most of these unknown parameters, sensing parameters to be estimated, now they become relative values. And they have image component, which means they are both positive and negative components, right? So the image components become a major challenge because we need to identify which one is the correct one. So these are the byproduct or the new problems introduced by cross-correlation. Several approaches have been proposed, and we also propose a technique called mirrored music algorithm. So conventional music algorithm, it only defines the base functions based on some exponential function, and essentially correspond to either positive or negative values, right? Because now we have image components in the cross correlation output, so we directly create the music bases, including the positive and negative parts. In this scenario, this allows us to directly get an estimate for the image components together with the original ones. So this significantly improves the accuracy and the efficiency. For details, you can refer to this paper. There's an interesting scenario here. For example, if we were only interested in estimating the angle of arrival, then we can directly compute the correlation matrix between the channel state information. And in the output of the cross correlation matrix, all the offsets will be removed. This actually corresponding to the cross antenna correlation, because we are exactly doing the cross correlation for signals from different antennas, right? So if we are interested in estimating the angle of arrival only, we can directly compute cross correlation matrix and then use, for example, musical aspirate to estimate these angles without needing to worry about the offsets. But in this process, we cannot remove the static components from such offsets. All right. Another class technique is called cross antenna signal ratio, or known as CSI ratio. We call it as cross antenna signal ratio because sometimes it doesn't need to be CSI that we use for following this approach. We can also use the receiver signal directly and calculate their ratio for sensing. Right? So we generalize it and call it CSR. So the idea is quite simple if we refer to a single dynamic path scenario. So if we have a single dynamic path, we can represent the CSI ratio in this form. Here, the HA stands for the static component, and the dynamic component only contains here, right? And of course, in the μ_d here, so μ_d is related to the spatial like antenna array response. As we mentioned, the angle typically changes slowly. So if we only want to estimate Doppler frequency, we can always assume μ_d is unchanged, right? So in this CSI ratio expression, only thing changing is delta nt here, right? When we have this expression, we know this is called as Mobius transformation. So Mobius transformation has a good property called period unchanged. If we change, for example, the values of delta, the signal may change, and we will get. So if we look at this exponential term, it's a 2D plot in the x and y zone or domain will be the red curve here. All right, it's a circle, and after it's plus c, it will be shifted toward this one, become the blue one. And if we calculate the reciprocal and multiply by bn, we get this one, the black curve. And finally, if we add a, it will be shifted to the purple one, the pink one. So the shape of the curve is unchanged from the original exponential term to the CSI ratio, right? This means if we can calculate the period of the circle, then we can approximately get the Doppler frequency estimate by estimate the change in the CSI ratio output. then the key problem becomes, okay, how we can estimate, for example, the central point of this observed CSI ratio angle, and then shift it back to the origin point, and then we can get the estimate for the Doppler frequency. All right, so this is a basic idea using CSI ratio for single dynamic target estimation. So this approach is very effective. Here we show 2 examples. So this example shows the scenario for the phase for the CSI ratio when there's no dynamic path at all. So the channel is purely static. Different colors are for the CSI ratio angle or phase for different subcarriers, right? So we can see this is static, unchanged almost. And when there's some dynamic path there, then we see the phase changes, right? So very clear pattern associated with movement. Actually, this corresponding to a person standing still while breathing. We can detect his breathing pattern using this simple and effective CSI ratio approach. Here is one more example. Here is one more example showing the measurements obtained from Wi-Fi devices. So similarly, we can see the dynamics due to movement of object. Right? So it's very clearly, if we only want to measure in particular Doppler frequency, so CSI ratio approach is very effective. The major, there's one major advantage of the CSI ratio approach, because when we calculate the ratio, we actually can remove some common distortions between the signals at different antennas, right? For example, the AGC effect. If we apply the cross-antenna cross-correlation, we cannot remove the AGC effect. But if we use the CSI ratio, then the AGC, because it's the same for different antennas, so its impact can be removed. This is one major advantage of the CSI ratio approach compared to cross-antenna cross-correlation. But one major disadvantage is now we have a nonlinear model because the unknown is in the denominator, right? So this becomes a nonlinear model, and the conventional, these classical spectral analytics that can be used for sensing parameter estimation cannot be applied anymore, because all those approaches can only be applied to linear models. In this scenario, it's very hard to apply this CSI ratio approach to multiple objects. Right? So how can we apply the approach? I skip this because I already introduced the idea just a while. And this result shows the performance for different approaches. So this is the cross-antenna signal ratio approach. We can see, although we applied some imaging suppression approach, we can still see many images of the actual desired ones. While the CSI ratio approach, it has very clear estimates for the Doppler frequency, right? Anyway, so one of the major disadvantages for CSI ratio approach is it's harder to handle nonlinear. It's very hard to handle multi-targets estimation because it's nonlinear. So to solve this problem, we introduce approach by using Taylor series to represent the CSI ratio expression. Right? So we extend it to a polynomial form, and then we keep several low-order terms, and then we can extend the music technique to deal with to estimate these sensing parameters in the polynomial forms. The CSI ratio approach, it's a very interesting one. This approach was originally introduced by a professor in Beijing University. It's called Zhang, and we did quite a few extensions based on their approach. And there are a lot of interesting observations that we can get if we look at the waveforms. So we may want to know, for example, how the different parameters of the signal models affect the sensing accuracy. For example, the ratio between the dynamic path power and the static path, and the SINR, and etc. Right. So these problems have been partially solved. We did some work to characterize the CSR ratio CRLB, and we reached several important conclusions summarized in this paper. If you are interested, you can go to have a look. Cross-frequency sensing has also been developed to extend the antenna-based approaches to the frequency domain. Originally, the approach was applied in the spatial domain, and we need multiple antennas, right? So if we only have a single antenna receiver, what we can do, all right? If we have a dominating path, we can simply extend the approach to the frequency domain by computing, for example, the cross correlation between signals from different subcarriers, or signal ratios, right? So we can similarly get the sensing parameter estimations. Of course, there are some differences because, for example, when we compute the cross correlation between signals from different subcarriers, we cannot fully remove the tau OK, right? The timing offset, because n is different. So we needed to develop some additional approaches to further tackle this issue. Right? This is not as straightforward as in the spatial domain, but this is still effective. Next, I'm going to introduce the idea for constructing a reference signal. So remember, the CACC and the CASR approaches, essentially they are using reference signal from the whole, for example, whole antenna, right? So those approaches, they do not introduce distortions, because this is based on original received signal. It doesn't try to create one which will typically introduce distortions, but they introduce multiple paths. Right? In some sense, this complicates the estimation. In the ideal case, if we can construct a reference signal, very clear, single path, then we can compute a cross correlation or ratio based on the observation and this reference path. And the output is only cross product between the reference path and the observed signal. Right? So this would be a much simpler output, but this is based on the assumption that we can create a perfect reference path. In reality, this could be challenging. Right? So I show you some examples, particular scenarios when this approach can be effective. Right? A good scenario is if we have a larger path, a single large path, and this path is stable over different time slots or snapshots. Right? So as shown here, this is the actual measurement from Wi-Fi testbed. They are measured across different time, and we can see there's often a dominating or relatively larger path, followed by several smaller paths. Right? So in this scenario, we can often create a reference path based on the dominating ones. There are several approaches. For example, the simplest one is we just apply IDFT to the channel state information in the frequency domain. and then we get a time domain one, and we can get the signals from the corresponding to the peak, right? So this peak signal is the time domain one. To use it to cancel the offsets, we then need to map the signal back to the frequency domain. This is simple. We just apply DFT to the peak signal, right? Then we get the reference signal at each subcarrier, and we can multiply or do division with respect to this reference signal to remove all these offsets. All right. So this is a simple yet effective approach. Another advanced approach is we can use compressive sensing to construct a time domain path. This is useful when, for example, the resolution, time domain resolution is low and the bandwidth is small, right? Because in this scenario, dynamic and the dominating static path, they may be mixed together. It's very hard to separate them. If we only use the DFT approach, the constructed signal may contain a lot of interference from the dynamic path, right? So make the signal unclear. In this scenario, we may adopt advanced compressive sensing approach, which is high resolution, to construct such a reference signal. All right. We can also use other techniques. For example, we use beamforming or use null space suppression to get the clean reference signal. So this slide shows one example where we apply the idea for creating reference signal based on beamforming to create a clean static path and use this path to remove offsets and estimate AOA and the other parameters for the dynamic paths. Right? So this approach turns out to be very effective if we can achieve good angle of arrival estimation for multiple paths. Another approach is called offset compensation, estimation and compensation, or alignment. So we first try to estimate the unknown offsets, and then we either cancel them, we either compensate for them, or we align with respect to them. Here is one approach. In this approach, we try to estimate the signal subspace, which is more reliable compared to using a single path. All right, we try to estimate the signal subspace and then align the snapshots with respect to the subspace. Once the CSI snapshots they are aligned, then we can get estimates, for example, for delay and Doppler shift. Right. Quite often, this approach needs to be combined with other approaches because it's very hard to realize sensing the parameter estimation for all sensing parameters in one go. Right? We typically need to combine multiple approaches when we use this offset compensation or align approach. Although the study on biostatic sensing has been advanced by, as I mentioned, 7 to 8 years, but there are still a lot of unresolved approaches. For example, current approaches are typically based on the assumption that there's a dominating line of sight path. Right? Although we have already achieved more promising approaches that does not require such assumption, still the success is limited. And also most of the work, they are based on the assumption that both transmitter and receiver, they are static. Right? So when there's a node is moving, then the problem becomes much more challenging. Also, multi-target sensing in biostatic setup is not well resolved either. So potentially a lot of research opportunities here. And once this issue is fully resolved, then we can realize sensing in almost all of the communication networks seamlessly with very low cost. Next, I show you some for projects and demonstrators. We have developed a Wi-Fi sensing system with integrated localization, biomedical signal extraction, and gesture recognition, etc. So Wi-Fi sensing, it represents a very good application for integrated sensing and communications in the indoor environment, right? Because in this scenario, the interference sources are small, and typically the number for targets to be sensed are small too. This is different to mobile network setup. Sensing in mobile network is often much more challenging because so many targets there. Next, I'll show you two videos. One is on two objects tracking, and another one is on biomedical signal extraction, in particular breathing pattern and heartbeat tracking. So when I play the videos, I also open to answer your questions. All right, if you have any. Thank you very much. Here is an acknowledgement to my collaborators and some reference papers mentioned in this talk. Okay, now let me show you two videos. The first video is about tracking, locating two objects. So this is based on use of two laptops with network Wi-Fi network card, and the transmitter and the receiver, they are blocked by a whiteboard between them. Right, they are separated by about 3 to 4 meters. This is quite short one. I extracted one segment, so let me show you again. So as you can see, the trajectory of the two persons, they can be very well tracked. There are two dots here. One is the benchmarking results from a radar, and another one is from the Wi-Fi. Okay. So another video, this is for biomedical signal extraction. Okay, I jump to the biomedical extraction part. So as you can see, these two plots, the top one shows the estimation for the breathing pattern, the respiration rate, and the bottom one shows the heartbeat rate. The setup is similar, transmitter and receiver here on the two tables. So the bottom ones, they show the sensing parameters that we estimated, Doppler, delay, angles, etc. So as you can see from the result, both of the breathing pattern and the heartbeat pattern, they can be well estimated at a different distance, ranging from 1 meter to about like 7 to 8 meters, either just in front of the receiver or behind the tables, etc. So even when the person lying down here, we can still see the result is quite good. Okay, thank you very much. Any questions?
Yeah, okay, thank you, Professor Zhang, for this impressive talk. So we have received some questions from the audience. So first one, Professor Zhang, as you stated that the clock synchronism needs to ambiguities in localization and the speed estimation. So how completely do these single receiver-based solutions resolve these ambiguities?
How, sorry, can you repeat the question?
So how completely do these single receiver-based solutions resolve these
How
ambiguities?
completely?
Yeah, yeah, how completely?
What do you mean, how completely?
I think the audience, perhaps he means, so how much can we reduce this kind of ambiguities to
Oh,
maybe 30% or yeah.
okay. Yeah, sorry about this. This is a very good question. Generally, if we adopt the cancellation approach, we can remove all of the offsets, right? But the cancellation approach, as I mentioned, typically it has some byproduct issues, like the doubled number of terms, unknown terms, or depends on how good we can construct the reference signal, right? Typically, we cannot get a perfectly clean path, even we have dominating random side path. So often we will face some residual interference, and really depends on many factors. If we have, for example, dominating path, typically the performance will be very good. And if there's no dominating path, in particular, even there's no dominating path between static and dynamic paths, then the issue becomes more complicated, right? But it's still possible. So in terms of removing offsets, we can certainly fully remove the offsets. It's just when we proceed with estimating the parameters, we often face interfering signals.
So which means that perhaps we can, if we have a perfect scenario, perhaps we can completely so resolve this kind of ambiguities, right?
Yeah, if we the cancellation approach, it will be able to fully remove the offsets. It's just as I mentioned, it will introduce new problem, right? Depends on how good we can deal with the new problem. Yeah, but it's always trade-off. Yeah.
So are there any experiments to show the maybe to what kind of levels we can reduce this kind of ambiguities?
For the we actually have a paper discuss the theoretical gap between bistatic sensing and sensing without any clock offsets issue, right? This paper was we probably didn't list it here, but it was the first author is Jing Bo from Beiyou PT. Yeah, so if you are interested, you can have a look at this paper. So we provided CIOB analyze the gap between these two scenarios. So this kind of provides a theoretical gap between them. I think the gap is probably less than 1 dB also.
Ah, I see. Okay. Yeah. Okay. Thank you. So there's another question. So because that we have considered the static offset in the, I think in this talk. So audience is asking how robust are the proposed solutions to dynamic and time varying clock drift?
Dynamic and
Clock
clock drift.
Yeah, yeah.
We don't really assume whether the clock drift is consistent or it's time varying. So almost all of the approaches I mentioned here, they are independent of the feature of the clock, right?
Yeah.
It can be time varying, it can be static. It doesn't really matter. So this means all of the offsets they can be time varying.
Yeah, okay. So needs they to be modeled as a time varying process, such as Markov, or
No,
it doesn't matter?
no. I think if we know the, for example, statistical property of is a variation, all right, we can exploit it. But in most of the approaches I mentioned here, they don't directly exploit the statistical property of the model variation. So, for example, it may follow some particular model, and if we want to extract, if we want to leverage such a model, we then need to base our sensing algorithm on the use of such a model. The conventional one, like Esprit music, widely used, they cannot exploit such a prior model. So you need to consider the use for example, compressive sensing, etc.
So I believe so. The proposed
Because
algorithm. Yeah. Sorry. Yeah, please.
yeah, I mean, compressive sensing definitely it's a very good sensing technique. It can, because it allows us to incorporate the prior distribution or statistical distribution.
Yeah.
So if you formulate the problem and you want to exploit the statistical property of the parameters like a delay or the Doppler, the timing offset, safe offset, etc. How do they distribute it over time? Then you can consider the use of compressive sensing. Yeah.
So even when the clock drift is time varying, so the proposed solution can still work well, right?
Yeah.
Okay.
I think the underlying technique it still applies. It's just how to integrate a technique like compressive sensing into the framework.
Yeah. Okay. Thank you, Professor Zhang. So that's all of the questions. Thank you so much.
Okay. Thank you very much. So our audience, thank you very much for your attention. If you have any additional question, you can always email me. But I think my email address is provided somewhere. Oh no.
Yeah.
Anyway, you should be able to find my email address.
Here.
It's here. It's here.
Yeah.
Yeah.
Okay.
Okay.
Okay. Thank you, Professor Zhang. Thank you.
All right. Thank you. Okay. Bye.
Bye.